Thank you for the introduction. So I'll talk about collaborative learning with limited interaction. So this is joint work with my former colleague Yuan Zhou, who is now at the UIUC, and our students Chao. So one of the biggest challenges in machine learning is to make learning scalable. So one way to do this is to introduce multiple agents and let them try to compute the objective function collaboratively. So one issue with that is that interaction between agents can be expensive, as we have learned in our daily life. So for software and agents, first, communication is very time expensive because of the network bandwidth, latency, and protocol handshaking. It also consumes a lot of energy, which is critical for a lot of applications. Just think about the exploration in deep sea and outer space. So we are interested in the trade-off between the number of runs of number of runs of interaction and the speed up of collaborative learning, which we will define shortly. So we will consider a basic question in reinforcement learning called the best arm identification in multi-armed bandits. So in this problem, we have n alternative arms, where the ith arm is associated with unknown reward distribution mu I. So our goal is to try to find the arm with the largest mean. Okay? So we try to do this by a sequence of arm pools, so that each pulse on the ith arm will give us ID sample from the distribution mu I. Our goal is to, in the centralized setting, is to minimize the number of the total number of arm pools. Okay. So let's assume that each arm pool takes a unit time. So there are two variants of this problem. The first is called fixed time best arm. So in this variant, we are given a time budget t, and our goal is to find the best arm with the smallest error probability. The second variant is called fixed confidence best arm. In this case, we are given the error probability delta, and we try to find the best arm with error probability at the most delta using the smallest amount of time. Okay? So we will consider both cases in this paper. So let me now try to introduce you our collaborative learning model. So again, we have n arms, and now we have k agents, as learning proceeds in rounds. So each round, at any time step, based on the outcomes of all previous pulls or message received, and the randomness of the algorithm, each agent takes one of the following actions. It can either make the next pull, or request a communication step and enter the wait mode, or terminate and output the answer. So a communication step starts if all the agents are in the wait mode, and then after the communication, the agents will start a new round of arm pulls. So at the end of the day, we require all the agents to output the same best arm. Okay? So the goal, we are trying to minimize these two things. We want to minimize the number of rounds R, and the running time, which is defined to be just the sum of the time steps of all the rounds. So the total cost of the algorithms actually can be seen sort of a weighted sum of these two values. The coefficients are unknown. This depends on the applications. So this is why we are interested in the trade-offs between R and T. So R is the number of rounds, T is the running time. Okay. So now let me introduce the concept of speed up. This is defined. So for collaborative learning algorithm A, so beta A is a speed up. I mean, this expression looks complicated, but basically this is just the running time of the ratio between the running time of the best centralized algorithm and the running time of the collaborative algorithm A. Okay, so we have this parameter T because unfortunately our upper bound slowly degrades as T grows, so in the logarithmic scale. Okay, so maybe this T can be, this dependence can be removed in the future. So we define beta KR to be the best. Basically, we consider all the collaborative algorithms that finish in R rounds, and with K agents, and we pick the best one. Okay, so now, so previously we talked about we want to study the trade-offs between the number of runs and the running time of the algorithm. Now we can instead study the trade-offs between the number of runs and the speed up of the algorithm. Okay, so clearly there's a trade-off between these two values. When I is equal to 1, basically there's no communication, then each agent has to basically solve the problem by itself. And in this case, speed up is no more than 1. Okay? And when I increase, this speed up will increase. On the other hand, like we always have the upper bound that the speed up can never be more than k. K is the number of the agents. You cannot hope to get more than k. Right. So here's the table of results. So there's a previous paper published in NIPS 6 years ago. So the study is basically the same question as we study, but it only gives some, so for the fixed time setting, it only gives some very special case when the number of runs of communication is 2. And for the fixed confidence setting, it gives the upper bound, which is like, I think it's easy adaptation of a centralized algorithm. And you can see that our result significantly generalizes and complements the previous result. So this looks probably a bit complicated. Let me try to simplify this for you. So let's focus on the most interesting case that we want a full speed up. It means we want to get the speed up of k using k agents. So in setting, we give up a bound showing that we can do it in, we can design algorithm only use log k runs of communication. And we also show this is almost tied up to a log k factor. For the fixed confidence setting, we show the previous upper bound is almost tied up to some log factor. Okay, so here delta mean is the mean of the best arm, the difference between the mean of the best arm and the mean of the second best arm, I mean, which is not known by the algorithm, but for lower bound this is fine. Okay, so let me summarize our contribution. So we give almost tight round speed up trade-offs for both variants of the best arm identification problem. And we also showed there's a separation between the two variants. If you think about if the delta mean is very, very small, then actually the fixed confidence case is more difficult than the fixed time case. This somehow indicates that if we roughly know like how much time we need, then it can helps to solve the problem, make the problem easier. Okay. And along the way, we also developed 2 techniques for proving round lower bounds in this collaborative learning setting, and we will talk about one of them in this talk. Okay, so this finishes the introduction. Let me now try to give you some technical details. So I will focus on our first result, which is a lower bound for the fixed time variance of the best arm identification problem. So a standard technique for proving lower bounds for multi-agents computation is called round elimination. So let me try to introduce the framework for you in the setting of our model, collaborative learning. So basically, this is an induction. Okay, so the induction step says that if there exists an R-round algorithm with some error probability delta R and the time budget T on some input distribution sigma R, then we can construct another algorithm which only use R-1 round with error probability delta R-1 and same time budget T on a slightly different input distribution sigma R-1. So basically, we save the 1 round of communication at the cost of increase the error probability a little bit. So sigma R-1 is a little bit higher than sigma R, delta R. Okay? And on the other hand, we also show that there's no 0 round algorithm with error probability strictly smaller than 1 on a non-trivial input distribution sigma 0. And combining these 2 items, we can show that any algorithm with time budget T and error probability, let's say 0.01, needs at least R rounds of communication. Okay, so basically it's an induction. So indeed, like Agova et al. In a code 17 paper use basically this random elimination technique to prove log star n lower bounds for best arm identification on the tight budget T, which is equal to roughly n over delta mean square over k for the non-adaptive setting. So by non-adaptive setting, we mean in each round, all arm pool should be determined at the beginning of the round. So this is what we mean by non-adaptive algorithm. And so let me give you like some feeling of the Hardings distribution they use, which we call one spike distribution. Basically, what they do is they basically pick a random arm and to be the best arm with assign it with mean 1/2, and the rest of the arms has mean half minus delta mean is some small value. Okay, so this is a hard input distribution to achieve this log star n lower bound. Okay, so the basic argument is as follows. So if we don't make, let's consider a single round. So if we don't make enough polls in this round, then conditional on the poll outcomes, the index of the best arm is still kind of uncertain, meaning that we can probably prune some of the arms, but for the remaining survival arms, we still don't know which arm is the best arm. So this is basically the idea. And more precisely, we have to show that the posterior distribution of the index of the best arm can be written as a convex combination of a set of distributions. Each of them has a large support of size at the most log n, and is close to the uniform distribution. So basically, it's close to the original distribution in some sense, but we reduce the number of arms after each round. Okay, and this way we can prove a log star n lower bounds, because we can do it log star n times, and then the number of n, the n will be constant. So this is what we can do. Okay. So, but we want to prove a much higher lower bound. We want to prove a lower bound that is logarithmic in terms of the number of arms. Okay, and to do this, we need to kind of use a better, more restricted time budget, so which is h over k. So h is defined to be the sum of 1 over delta I square. Delta I is the difference between the mean of the best arm and the mean of the I's best arm in the input. Okay, so this is h is actually achievable. Tilde h, I had some log factor here. Tilde h is achievable in the centralized setting. Okay, so and the distribution we use is different from the one spike distribution. We call it the pyramid-like distribution. So roughly speaking, we take half of the random arms and assign them with mean 1/2 minus 1/4, and then n over 4 random arms with mean 1/2 minus 1/8, and n over 8 random arms with mean 1/2 minus 1/16, and so on. Okay, it's like a pyramid. So like at the beginning, we try to see like if we can follow the argument of the previous paper, but the technical challenges, in principle, I think it is doable, but technically it's very difficult. It's not clear how can we decompose the posterior distribution to a convex combination of a set of distributions, each of which is close to the same pyramid-like distribution, so which is much more complicated than the one spike distribution. So there's some technical challenge here. So this is why like we try to come up with some new ideas. So the new idea we have is to try to generalize the standard round elimination technique. So this is a framework. I mean, it looks very similar to what we have seen like a few slides ago. The only difference here is that instead of, so we replace like a single distribution to be a class of distributions. So what's the benefit of this? Now we don't have to show that the posterior distribution nu prime of nu is close to a particular distribution. We only need to show that the new posterior distribution belongs to the next class of distributions. Okay, I hope this makes sense to you. Okay. So this is how we choose our hard input distribution class. It looks complicated. Let me try to explain a little bit for you. So the input class, input distribution class, dj is defined as the following. So for each distribution in this class, it has support b to the power minus 1, b to the power minus 2, to b power, to the power minus l. So b is a Poilog factor. L is basically log n over log n, which is the number of rounds, the lower bounds we want to prove. And so for each, if x is distributed according to mu, then this is its distribution. So for L from J to L, the probability that x takes value b to the power minus L is roughly b to the power minus 2L. And lambda J is a normalization factor. And the tail is basically negligible tail. So basically the mass on the on b to the power minus L, where L is less than J, is negligible. Okay, so then we pick each arm RID with mean 1 over 2 minus x. X is distributed like this, and basically we try to embed the pyramid distribution into each arm because this will simplify our analysis to make things RID. If we just pick a pyramid distribution like what I mentioned before, the analysis will be more complicated. Okay, so what's the key property of this input distribution class? So let's consider an arm with mean 1 over 2 minus x, where x is distributed to according to some distribution in this input distribution class dj. So if we pull the arm, gamma times b to the power 2j times, this is some threshold, okay? And then let theta to be the pull outcomes, and the absolute value of theta is just sum of the theta i's. So we can show that if this absolute value of theta is not in some boundary, we put some additional, for technical reasons, we say that if the absolute value of theta is not in this particular interval, then we publish the arm. Okay, so we can show the following. So if let nu to be the posterior of x after observing this sequence of pull outcomes, if the arm is not published, then we must have that the posterior distribution nu belongs to the input distribution class dj plus 1. Okay, this is how we actually do the induction. So for non-adaptive case, this is our result. So the argument is basically plugging the generalized round elimination technique with this. So here, instead of talking about running time, we use this speed up. Basically, it's the same thing. And the input distribution is what we have chosen for, we discussed like a few slides ago. Actually, last slide. Okay, and we also prove the base case, like if there's no communications round, then we cannot succeed with good probability on the distribution dl over 2. So basically, we just the plugging of the framework we mentioned before. So yeah, because of time, I probably will not go to the technical details of the proof. So let me talk a little bit more about on the adaptive case. So for adaptive case, we can show, so lower boundary proves is log k over log k. So ignore the alpha thing. Okay. So intuition is that when the number of arms is smaller than the number of agents k, then adaptive pool do not have any advantage against non-adaptive pools in each round. And we can prove this by a coupling argument. We compare the behavior of the adaptive algorithm and with that of a non-adaptive algorithm. Okay? So because of time, I'm not going to talk about the details of this coupling argument. And again, like I will leave the, I will not talk in details about the other main results we have, so the upper bound for fixed time case and the tight lower bounds for the fixed confidence case. Okay, so let me briefly summarize this paper. So we conducted a systematic study of the best arm identification in a setting of collaborative learning with limited interaction. And we give almost tight bounds, almost tight around the speed-up trade-offs for both the fixed time and the fixed confidence setting. And along the way, we developed two new techniques for proving around lower bounds. What we are excited about the paper is like we think this probably opens a new research direction on communication efficient collaborative learning, and there are many other problems that can be studied. For example, regrets, which is another fundamental problem for bandits, and we can also talk about think about general reinforcement learning problems. Okay, so that's all I want to say. Thank you. Yeah.
If you want worst case, is it again the longest star and is the correct answer? Or?
Yeah, because yeah, that's right. So I should mention, like, this H is called the instance complexity of the best arm identification. If we relax this to the bound you guys have is n over delta mean squared, then it's again log star, and yeah. Sorry? Yeah, it's equivalent to the non-adaptive case of our model, but we first prove a lower bound for the non-adaptive case, right? And then we try to extend it to the adaptive case. Yes.